Around 2018, 2019, there were these methods called saliency maps or heat maps. They basically just take your input and they say your model is focused on input 1 or input 2. And the idea is that you can then show this heat map to a human and say, this is what your model is doing. But it turned out that if you completely randomize the model and sort of mess up the weights of the model, the heat maps don't change. And so a lot of postdoc tools face this challenge where if they're not as granular as possible, they're not able to be effective. But as you try and make a postdoc tool more reliable, the things you end up doing start forcing you to change the way you train the model. And so this insight was what sort of informed my co-founder and I to sort of say, okay, it seems like the way you get reliable interpretability is to change the way you train your model.
Julius, thanks a lot for joining me. Maybe starting off, you can tell us what Guide Lab does.
Sounds good. Thank you for inviting me here. Guide Labs, we're building interpretable models. So right now we're very focused on large language models that are more reliably explain their reasoning. So to give you an example, we want for every model, every output it gives to be able to trace that output to its input, any inputs in its context, to humanly understandable concepts in its representations, and to its training data. And the goal of this is so that you can more reliably understand what the model is doing, why it's generating any group of tokens it's generating, and for you to be able to better audit, understand, and align the model. So that's sort of our high-level focus. We're building these models to sort of target it at people that are very interested in understanding why is my model generating this output, and what can I do to change it and control the output of the model.
So historically, why has interpretability been hard? I know that's a bit of an open-ended question, but
Right. There are a few different reasons. I would say maybe to give you a background on the style of interpretability we're doing. Right now, mechanistic interpretability is very popular. So the idea is I give you a model like Llama 3, 8B, or DeepSeek model, and then you tell me what part of this model is sort of focused on basketball or sports, and how can I get it to start talking about sports? Or one of the things we've seen like with sycophantic models where you ask the model a question and then it immediately respond, yes, you're right. I should have suggested what you're asking. What makes interpretability hard is that when a lot of the most kind of techniques people use, you wait until after you've trained the model before you start to control and try and understand it. But a lot has already got into the process, the training data, the model architecture, the training process is completed. And now you're trying to sort of do neuroscience in some sense to find which part of the model is sort of responsible for the output. And those models have billions, trillions of parameters. So it's usually very difficult for you to localize the behavior you want. And so I would say there's sort of a technical reason. It's very difficult to localize information in these models. And then another one is just maybe a structural reason. Most interpretability researchers try not to sort of get involved in the training process of the model. It's just give me a model, I'll do some work on it to figure out what it's doing. But it tends to leave a lot on the table. And so you often need to sort of patch up the work you're doing. And so the challenge is here, I think it's more late intervention, and the techniques are not quite reliable enough yet to always sort of work when you need them to.
Yeah, I mean, from the outside, like as someone who's a researcher, it almost sounds like it's, in ways mildly counter to some of the insights of machine learning generally, right? That we give a system enough samples and it's better than humans at things. And so it's like maybe intuitive that we don't actually understand what's going on inside.
Right. Yeah, actually, you speak to a very important point. So I think the deep learning revolution, the way you sort of phrase it is, you give me your data, I find the biggest neural network I can, I will train it on this model, usually a transformer architecture, and the model will sort of learn to sort of find all the correlations and all the things it needs to know. The challenge there is that when you don't guide the model's process, when you sort of don't inform it, you have to now come back and say, okay, I've just given you 1 billion weights, figure out what it's doing. I've just given you 1 trillion weights, figure out what it's doing. So in some sense, the interpretability challenge is sort of counter to the deep learning sort of revolution that says, give me the largest transformer possible, give me as big data as you can, I will just set it off and let it run. What makes sort of normal deep learning training easy tends to be what make interpretability challenging, because you sort of have to battle the constraints that interpretability wants to impose against the, I don't want to interfere with the training process that deep learning sort of encourages.
It's almost like if you knew what to do beforehand, you could do it procedurally in the first place, and you wouldn't need machine learning. And so that's why everyone's like, all right, let's do this post training.
Right.
But you're coming to the problem from a very different perspective. Like, what is your background, and why did you decide to approach interpretability this way?
Right. And so, very good question. So my background is as a machine learning researcher. So spent a lot of my time doing a PhD in interpretability. And even before that, I sort of came into interpretability from a sort of auditability aspect. So before going into my PhD, in 2017, 2016, there was a lot of work about how sort of at that time, small neural networks that were sort of 25 million parameters, 50 million parameters, people were applying them to like chest x-ray to sort of decide whether or not you get a loan or not. And so there was all sort of a hoopla of how are we going to regulate machine learning? At the time, how are we going to regulate machine learning? Now it's how are we going to regulate AI? And so it was, how are we going to regulate these models that are being used for sort of consequential decisions? And the challenge there was, can I trace the give this person a loan or not decision that a model is making to what part of the network or what part of the training data? And so that's how I actually came into the field. And there I was sort of trying to understand the techniques that people were using to do this. And so for, I would say, 6-7 years, a lot of the research was sort of pursuing sort of this postdoc work. And I would say only in the last 3-4 years have there been sort of breakthroughs that show that there actually doesn't need to be a trade-off. So I think one of the things the way people convey it is that there's a trade-off between interpretability and performance. If you want a really high-performing model, it's going to be interpretable. Or if you want a very interpretable model, it's just going to be a weak model on the benchmarks. And so for a long time, this has been the prevailing wisdom. And the way sort of I came to this was as part of my PhD, we did a series of papers that show that you can actually train these big neural networks, constrain them while you're training them, and then still have them match the performance of something that was not constrained ahead of time. So I would say that's sort of the counterintuitive insight. And there's also a long sort of process of, I would say, pain that led to this, which was that a lot of my PhD was actually looking at these postdoc tools and saying, how effective are they when we actually want to reliably explain? So to give you an example, around 2018, 2019, there were these methods called saliency maps or heat maps. And what they do is they basically just take your input and they say your model is focused on input 1 or input 2. And the idea is that you can then show this heat map to a human and say, this is what your model is doing. But it turned out that if you completely randomize the model and sort of mess up the weights of the model, the heat maps don't change. And so a lot of postdoc tools face this challenge where if they're not as granular as possible, they're not able to be effective. But as you try and make a postdoc tool more reliable, the things you end up doing start forcing you to change the way you train the model. And so this insight was what sort of informed my co-founder and I to sort of say, okay, it seems like the way you get reliable interpretability is to change the way you train your model. Can we show that if you change the way you train your model, you also don't get this performance degradation? And so that's how that we went on that journey.
I guess I do want to double down on that, but like, I guess circling back a little bit on the problem space, like there is like the example you give of, things like, credit approval, like it does seem like there's just this long history of there's just something deeply unsatisfying for humans about black box machine learning models, and not even just machine learning, like even like linear regressions that we don't have intuitions around how they work are like upsetting to us in some ways, because like we have this feeling of agency around decision making that's like very important to us. So like when you talk about like what you want to achieve, like how constrained is interpretability as a concept? Like, is it ever going to be the case that like a human has strong intuitions around a multi-billion parameter model and what it's doing internally? Or is it like, the best we can do is like a concept here or there that is influential on this outcome?
Right. No, I think you're getting to a good point. I think this is also something the field struggles with. What level of interpretability is really enough for a user to trust a model? And in some sense, actually, any model is interpretable. It's how interpretable it is. And so what barrier are you willing to overcome for you to be able to sort of say you understand the model?
There's like this qualitative aspect of intuition.
Right. And I think there are different sort of levels at which you can sort of say this. One way is to say you understand a model when you can change the model's output, when you can intervene or poke around with the model to be able to control its output. And it is true that there's lots of systems you and I rely on where we don't understand what it's doing, but we sort of delegate that understanding to someone else. So maybe you get on an airplane, you might not know how the airplane works, but there's some person at the FAA whose job is it to understand or validate the airplane. And so I think the equivalent doesn't yet exist for this models where there's a set of techniques, there's a set of tools that we're able to really sort of poke the model. So here I would say the kind of understanding you can aim for, at least with the current tools, is to say what training data is the model relying on, and then you might sort of have to do some inspection of this to glean what factors the model is using, what concepts. I think their concepts are particularly sort of a good test bed because the model is sort of releasing tokens in sort of human understandable settings. So you can just think of it as a translation of the model's representations into natural language that you and I can understand. And hopefully that sort of gives you more trust. So let's say you have some LLM where you say, okay, here are my symptoms. Do you think I have appendicitis? And if the model responds and all of the training data it's using is a bunch of blog posts from people that are not medical experts, then maybe you have to look into the answer a little more carefully. But if you see now that the things it's referencing are maybe WebMD blogs or sort of specific sort of scientific articles that relate to what you're asking, and then maybe you have more trust. So I think the level of interpretability you get depends in some sense on what the task is and what you're trying to get the model to do. But the operative ways we sort of think about it is, are you able to control the model's outputs? So if I tell you you have appendicitis based on the symptoms you have, if you then sort of remove the symptom or you tell the model not to rely on the training data, does that change? If it doesn't change, then maybe you don't understand why the model is making its decision.
Yeah.
So we sort of see it as that way.
Yeah, that's interesting. There's this kind of high level, perhaps philosophical interpretability questions around like how human thinking maps to the models. But there's all these also like, once you're able to control concepts in the system, there's these very practical downstream outcroppings, which one is, this very deep, seems like this deep relationship between interpretability and controllability, but then also some of the things you're talking about sound like accountability.
Right. There's sort of accountability or like trust or being able to sort of verify or trace the model's decision. In some sense, I would say these are like downstream effects of interpretability. They don't necessarily have to be AI safety, accountability, or traceability. They just are things that interpretability should, like reliable interpretability should sort of make those easier.
Okay. All right. So jumping around again back to kind of where we're at. So like you became, at some point in your research, you became high conviction that like this had to happen at training time and was possible to do without a performance trade-off or or at least a small enough performance trade-off that it was worth it or both. And like, what was that moment like? Like what convinced you of that? Was it things that were happening in research or?
Right. So I think it was an evolution. I don't remember as like a single moment. One of the things that happens with interpretability research is that interpretability just tends to be one or two model generations behind. So it's either, let's say for a while, I would say between 2018, 2020, it was more this sort of deep vision model. So like Resonant 50, maybe some like bigger dense nets. That was sort of what most people in interpretability were focused on. And then around the time GPT-2, GPT-3 came out, people started doing interpretability work, translating some of that work to sort of LLMs. And then, of course, GPT-3, 3.5 comes out. And now the work you did on the vision models or on GPT-2 now doesn't translate to GPT 3.5. GPT-4 comes out, maybe it renders all of the research that we've done over the past 5 years sort of useless. So I think the idea of moving to training time interpretability sort of was a combination of being always behind the latest generation of models. Meaning, if you spend 2 years sort of perfecting a technique on Resonant 50, and then 2 years later GPT 3.5 comes along, and your technique is now useless, why not sort of use your technique to build a better model than GPT 3.5? And so I think that was one of it. The second one was sort of the pain I mentioned before, where I'd sort of spent several years sort of comparing methods or trying to come up with methods that don't interfere with the training process, and say, I don't want to mess around with the training process or fine tuning. I just want to apply this magical technique to the model and automatically have tell me what the model is doing. But I think what we sort of realized there was the models were the ones actually training them. So it's not like a human brain that somebody just hands you and say, sort of figure out what part is responsible for what. We actually have more leverage where we can control the model towards things that are more interpretable. So I would say it was a combination of that and sort of being the right time. So I would say there was a factor of the scientific insight of reliable interpretability requires sort of intervention at training time. Another one of sort of always being 1 to 2 generations of models behind. Yeah. And then the third one was just doing initial research. We wrote a paper in 2023 where we trained a few generative models and we showed that there wasn't a performance gap. So sort of stepping back and looking at those three and then realizing that most places sort of don't have enough high conviction to go after the idea. And we saw something that most people in the field didn't necessarily see yet. So a combination of that was what sort of made us sort of commit around that time.
Yeah, that's interesting. Because it's one trend I heard is that, like, we've talked, I know you and I have talked before about just the scope of doing it post-training is always so daunting, but it sounds like there's just this practical aspect where if it's not in the architecture, it's not going to scale up with the next generation, and you're starting from scratch. And so you get to the point where you start to believe that if we don't re-architect things, it's never going to happen, or at least in a robust enough way. And if you see enough signal that it probably will work, then it seems like worth trying. So with that, you started a company, and like, what did you do from there? And maybe kind of catch us up to the present.
Right. So we started a company at the end of 2023, early 2024, and we joined YC 2024 batch. And so as part of joining YC, it's because our background is as researchers, and we sort of had this insight, and we wanted to sort of say, okay, how do we bring this insight to market? And so we joined Y Combinator, and as part of that, we sort of started working on initial models to sort of train initial models to sort of demonstrate this insight. So our first sort of set of models we worked on was in 2024 to sort of show you can scale up to billions of parameters with interpretability baked in sort of a concept level fashion. And the goal there was to sort of show an order of magnitude advance over what people already done. So we went through YC winter 2023, and then we connected with Initialized, where we sort of came on board. And the goal there was to say, now we've trained our first model, and the first model was more the sort of 3 billion parameters, 5,000 concepts, to demonstrate the fact that we can actually sort of scale the methods we want. And that was sort of the initial insight. And after that, we wanted to then say, okay, let's scale it up, because as I said, there's this constant pushback about training time interpretability that you can't simultaneously have that and have a high performing model. And so we then decided, let's go for a non-trivial size and a non-trivial capable model. And so since then, we decided to assemble a team. So we're now a team of 9 people. assemble a team of like researchers, 5 researchers, 3 engineers, and 1 business and operations person to also work with us and say, we're building a 8 billion parameter model with sort of thousands of concepts, known concepts, and then also hundreds of thousands of unknown concepts that we can then reliably control in the way that I sort of mentioned earlier. So we've sort of gone from a series of small models in 2024 and sort of thousands of concepts now to sort of hundreds of thousands of concepts, both known and unknown, that we're able to control at the 7 and 8 billion parameter model scale.
And you, I guess to my understanding, like the techniques sort of generalize across different types of models, but you focused on language models mostly because those like easiest to benchmark against existing models, or like what was your thinking?
Right. Actually, so the first paper we wrote on this with A.A. Ishmael, who's our chief science officer, was in 2023. And there we actually focused on image generative models. And the techniques from there is what we're now translating to language models. One of the reasons why we pick language models is because it's one of the areas where it's sort of most difficult, where sort of a lot of training time interpretability hasn't really penetrated language models. There it tends to be in fine tuning and in sort of post-hoc correction. And we sort of saw this as a clear grand challenge for our techniques, that if we nail this, there's no more doubt in sort of our minds. There's never really been a doubt in our minds, but there's no more doubt in sort of, we can demonstrate to the field, like, look, we can train a 8 billion parameter model with sort of thousands of concepts or hundreds of thousands of concepts, and you can reliably control them. So we picked this sort of billion parameter LLMs because they represented the, in some sense, a big challenge for the kinds of methods that we're using.
If you can perfect it on large scale LLM,
right.
It should generalize to whatever you need to.
Right. And the techniques, we've sort of applied it to this image generative models, to protein language models. Protein language models are sort of very similar to like BERT language models. Instead of next token predictors, they tend to sort of, you mask out a sequence and then predict what you masked out. And so we've applied it there as well to a series of those. And so that was what gave us conviction that we can go after sort of larger scale LLMs, where they're also more useful in some sense, more broadly applicable. People use them across a variety of tasks. So that seemed like a good sort of avenue.
And when you started on a language model, you started with the next token predictor model?
Yes. We did start with the next token predictor, and the series of models we also trained in 2014 were also all next token predictors. And we started with that basically because that's the dominant paradigm. There are other paradigms, but that's the sort of dominant paradigm that everybody was going with. And we wanted to basically say, all right, our techniques are plug and play regardless of the architecture or the training paradigm that you want to use. Since then, we've sort of moved away from next token predictor, even though our techniques apply to that, but that's sort of what paradigm we started with.
And what do you switch to and why?
Good question. So there's sort of an emerging paradigm of sort of diffusion language models. So diffusion language models are also very popular in image generation. So I would actually say in image generation, they're the sort of dominant paradigm. They're like what next token prediction is in image land, where you can, I think the early versions of stable diffusion were all sort of trained with this paradigm. And so there, what you do is instead of predicting the next token, you actually mask out, you take a sequence, you mask out a part of your sequence. You can either mask out blocks or blocks of sequence, or you can mask out sort of within a block. And then you predict what you mask out, or in some sense, you unmask what you sort of mask. And here, what is different is typically you're unmasking multiple tokens at once, so gives you more control. And it also allows you to sort of generate multiple tokens at once if you train it in the right way. And so what this gives you is, it gives you a little bit more control, and it allows you to also sort of have a more long range dependence. There's an issue with a lot of next token predictors where if they see things in sequence, so if they say maybe the capital of France is blah, if you then ask it, is blah the capital of France, it sort of tends to fail on this kind of task. And so people call this the reversal curse. And a lot of next token predictors all have this issue. But diffusion models completely avoid this issue. So I would say there's a few reasons why we move to them. One, you get a better level of control because you're unmasking multiple tokens at once. So you're able to say, sort of, I want to get the model to not generate, let's say, toxic output. If I'm unmasking multiple things at once, I can get better control.
And there's like kind of an intuition that most things you'd want to control impact a bunch of tokens.
Right. Impact a bunch of tokens. So higher level of control sort of also fits with our theme more in terms of allows us to demonstrate sort of interpretability at a higher level as well.
Yeah, but you also believe that diffusion models are very promising for the future of like language models generally.
Right. And there's a few demonstrations that also make it clear. I think the pushback on them have been that they might not be inference, might not be as fast, but there's a Gemini inference model, there's a Gemini diffusion model, there's a model out of Mercury where you can make these things actually much faster than next token predictors. And so the reason why we sort of firmly believe in this direction and can bet on them is that, one, they give you all of the benefits of next token predictors, and then you get the added benefit of a lot of the interpretability techniques you want to allow you to more better control them. So for example, with image generation, you can say remove glasses, put black glasses back on, put a hat on this person, remove a hat. A lot of those control type techniques struggle when you port them over to next token prediction. And so moving to diffusion allows you to just get better control and you don't sacrifice any sort of benchmark performance. So it's just, in our view, it's sort of a strictly better paradigm than what we currently have. And it's also a better test bed or a better foundation for the interpretability techniques that we have. So we're sort of betting on them pretty strongly.
And then in building these, I mean, it seems like there's a decent amount of like, you know, you're doing a little bit of research, but a lot of engineering also to like actually play it out. Like what have there been anything that surprised you and how hard it was, or like what is really difficult about scaling this up?
Right. No, there's several things. Maybe to give you a sense, I remember reading the GPT-3 paper, and at the time, sort of as a sort of being in just my research mindset mode, the take from a lot of my friends and I was like, oh, they just took GPT-2 and trained it on more data and they scaled it up. And so there was this little bit of this was just all pure engineering. I think having now been in the process, I now see that it's substantial difficulty because a lot of research techniques have there's a non-trivial amount of work to get it to scale reliably. And typically you want a simple technique that you can use to scale. So I would say scaling interpretability in the way that we are hasn't necessarily been done before. And we're sort of the first that are doing this kind of work at that scale. So with doing anything for the first time, you hit all of the challenges that no one else has seen. So for example, if you look at most sort of research and papers, the number of concepts people usually do, 200 concepts. Maybe if they want to sort of go crazy, they do 1,000 concepts. And we do several order of magnitudes higher than this, 50,000 concepts, sort of millions of unknown concepts. So this kind of order of magnitude sort of shift basically makes it so that you have to rethink every step of the pipeline. So if you have 200 concepts, you can just sit at your table for like 3 hours and look through each one and sort of check if it's good. If you have 50,000, you have to sit at your table for 6 months. So
you need additional systems to verify that interpretability is interpretable.
Exactly. And now you need to check that system to make sure it's not it's sort of reliable. So we've found that scaling things up sort of brings new research questions that we have to sort of solve at scale.
Yeah. I mean, it's just a hard problem to like sort through all the concepts and figure out how you would evaluate them individually. Right.
So we have to also automatically evaluate them as well using models, using sort of classifiers and other things.
And so then you're having to come up with your own kind of benchmark like things that like measure like broad base.
Yeah. To sort of give you an example. So a lot of the time what people do is they annotate their data with concepts. And so, but it's easy to check this if you're annotating with 200 concepts or something like this, you can reliably get good metrics. And we found that when we sort of scale this up, so we initially scaled this up in 2024 to 5,000. That was still quite manageable. If you scale this up to 50,000, now you need more reliable way to sort of automatically do this. And a lot of the metrics we were initially planning to use completely just broke down. So we had to rethink these metrics from scratch and say, how do we automatically evaluate this? And a lot of that involves actually using LLMs and sort of gating them in the right way to make sure they can evaluate those concepts.
Yeah, like you're doing a bunch of programming that lives outside of the actual model training architecture. Right. How do you, I mean, have you run anything you weren't sure? Like have there been points where you're like, this might not work, or, you know, I'm worried, or what?
Yeah, there are several points. I think we started off with having a scaffolding of the idea. Usually the challenge comes in training the models. They can be, a little tweak can make them unstable. And so you often have to sort of say, we have the scaffolding, here are the 3 things we know we need. To what extent we know we need them, we're not sure. So a lot of the time you have those loss functions people use to train them. And the way we do sort of interpretability training is we basically add interpretability loss functions. But if you just add this in a naive way, it makes training unstable. So you have to sort of do a lot of hyperparameter search to say, which specific thing do I need? How much do I weight this interpretability loss so that it doesn't actually sort of make my training unstable? So several times we have to go in with an initial scaffolding of the idea, and then it's now, okay, let's sort of search for what instantiation of this idea actually will allow us to train well.
Yeah, because so much of the rest of the architecture of neural nets is like this lore that people have kind of figured out, a lot of best practices too. Right. And you can't just bring in people who know how to do that. Right. You kind of have to like relearn the constituent parts of it.
Right. And actually, this is one of the big challenges we have, which is there's a lot of best practice for training normal models where they'll say something like, this type of layer trains well when you do X, or maybe put layer norm here, or change this, normalize, if your data has this kind of behavior, normalize it in this way, or if you want this kind of invariance, use this kind of layer. When you're now doing interpretability training, those best practices basically don't exist, so we have to sort of go find the best practices. And one of the funny things about even normal deep learning training, there are papers that will often say, we find that this layer works or this technique works, but we don't know why. It's because of divine benevolence or something like this. And so we're also going on that journey ourselves to say, okay, we want to apply these 3 things. How do we put them in the right way to make sure they work?
Yeah. Does that heavily impact the cycle time of your training? How do you balance that with, moving, being a fast moving startup?
Right. I think the trick we've found so far is we sort of set a minimum bar. Very often there's a bar that we want to hit, which we don't often hit immediately just because we have a high bar for interpretability. But you can often match performance with just a minimum interpretability penalty. And so we just usually say, let's sort of get something working. Let's see how much we can push it. And then once we have an initial working prototype, then we try to push it. And if things start to become unstable, we know we can sort of go with some prototype. But there are times where there's an idea we want to get to work, where we know there's a variant of that idea that works, but we just haven't put it in the right form. So there we often have to like table it and say, this will be model 2, this will be model 3. For example, in the first set of models we trained in 2025, we wanted to actually have it so that we could have hierarchical concepts, where that, these 3 concepts all come together to form this high level thing, the way you have in sort of a lot of fields. But this tend to be very tricky to train. So we had something sort of working, but it wasn't training reliably. So there we had to make a hard call to say, okay, we'll table this for a future version of our models.
Yeah. That's also a weird one because you sort of expected that some of that happens naturally because these concepts are literally hierarchical or in real world to some extent. Right. So the representing them, you get some of the benefit even without the representation, I would assume, but it's an interesting thing.
Right. So we often have to like leave a few ideas off the table. And this goes to a thing where I often get the question of, how open do you be? Should you be about the kind of techniques and approaches we're sort of talking about? And I think at least at the moment, we take the stance of like, we can be open about what we're currently doing because the challenges in this space are so sort of big and there's so many questions that no one organization can answer all of them. And so the more people sort of trying to attack those questions, the more it makes it so that these interpretable models are sort of more popular.
Yeah, and in some sense, like the IP is like what the learning's getting you there.
Exactly.
Are as important as the any given generation's end product.
Right. And you get this sort of best, sort of what are the best techniques along the way. So instead of for somebody trying to retrain our model, they have to learn all of the sort of this thing doesn't work, this works, sort of the trade-offs we have to make on the path to the model. And that you often can't just get by reading a paper or by hearing somebody saying it. You sort of, there's a sort of training you have to do to sort of get that. So I think, and it's still also open how much some of these are instantly translatable to other people's settings. And so we think it's important that other people sort of come join us and try and attack this kind of questions.
We talked before, you recently had like a data issue that I thought was pretty interesting in terms of being instructive about like what's like what can randomly go wrong and when you're doing something that's new. Maybe take us through that.
Right. So one of the things we do is we sort of take a data set, and because so let me just set the background. For our models, we want to be able to say when the model is making this prediction, it has like this group of tokens or a paragraph or a chunk. Here are the most important concepts that the model is sort of relying on to make that prediction. And so very often the choice of our pre-training data is a very big deal because it determines the quality. Even no matter how good our losses are, the choice of the data determines the quality of the model and a variety of all kinds of things. So the issue we hit was that we had initially made a choice for a pre-training model. And I won't say the name of the data set because it's a big organization and I think they're doing good work, but that data set had a lot of duplicates in it. And so what it meant was, and not just normal like high quality duplicates, but you had a lot of duplicated spam articles. So if we train the model in multiple passes over this data set, it makes it so that your model is sort of not getting as many high quality samples as it should need. And we discovered this not as early as we would like before we set in motion all of our pipeline. And so we had to rethink, okay, this data set is something that's sort of standard that most people are using, but it has a lot of duplicates and it can actually lead to sort of substandard results. So should we sort of jettison this and move to a more smaller data set but higher quality? And so that was a trade-off we had to hit, and we discovered this sort of later than we'd like, and so we had to sort of transition from that to this new data set. But yeah, I think that's one of the things you don't necessarily account for ahead of time because our focus has been primarily on this interpretability losses and how do we train this model reliably at scale. And we just assumed the data sets that we're using were sort of, in some sense, perfectly deduplicated, but it turned out that they had some issues there.
Did you at all find it like somewhat validating of your approach, and that like you've gone like layering on interpretability and moving to diffusion made it obvious to you that the data set wasn't as useful as it maybe otherwise people thought it was?
Right. I mean, that's not how we discovered it, but it does map to exactly what we need because a lot of the diffusion models, at least this hasn't necessarily been conclusively proved, but one of the things that's been empirically noticed is if you have very high quality data and you're able to do multiple rounds on this data, you get more out of it from a diffusion model from a performance perspective than a next token predictor. And so that's one of the things that also worried us is that if we have this data that has a lot of low quality subsets that are then duplicated several times, doing multiple passes on it with our diffusion model will sort of hurt us more than would hurt a next token predictor. So in some sense, it maps with the direction we're going with, and it allowed us to quickly make a correcting decision in that case. And so that was a case where it was actually helpful that we had a high conviction in the diffusion direction to be able to make that correct.
Yeah, I mean, but at the very least, interesting that if you're doing something novel enough, weird things break that you take for granted.
Right.
Are you? I guess it's interesting. I've talked to a bunch of teams, and there's like a little bit of discrepancy, and it kind of often comes down to like what people are actually doing and how novel it is relative to like whatever corpus these big LLMs is trained on. Like, are you using AI coding heavily internally these days?
Some of us are actually, our team is sort of goes from people that are very experienced, they've been sort of coding for decades, to sort of new grads that are coding for the first time, or people that are just transitioning into machine learning. So I think our team uses pretty heavily coding tools, but sort of scoped to sort of task-based, not necessarily sort of writing the entire pipeline from scratch with LLM tools, but sort of assisted. So several people on the team use Cursor. I think a few use Claude Code, and usually, especially for data processing tasks, it's sort of very effective and sort of data pipeline, this kind of thing. And I think the places that is a little bit more challenging is research, sort of validating your research or getting feedback. Some of the models are very confident, usually if you see them in the right direction, they tend to give you sort of more sort of reliable feedback. If you say, okay, here is the technique I'm planning to try, sort of tell me all the things to look out for in this. Some of them are quite sophisticated, but it also has a downside of very often they sort of are relying on the more popular post-training interpretability corpus. So their response is like, what you're doing will not work. And so you sort of have to be very clear about the kind of research questions you're asking them. One of the things that's actually been popular with the sort of research community is that people just upload their research papers to the LLM, and then you ask questions about the paper the same way you ask about a PDF. But yeah, we use LLMs quite a bit in the company, so that especially coding LLMs.
Yeah, that makes sense. And there's a bunch of like day-to-day tasks where it's very useful, and
Right.
you kind of push the limits on the other end.
Right.
All right. I think that you're training a model now, I believe, and I imagine it'll be out by the time we release this episode.
Right.
So, what can you tell us? Like, I guess so it's a little premature for you to know the exact results, but what should we look forward to generally from Guide Labs?
Right. So I would say this model is to demonstrate a few things. The first one is one of the things we talked about there's sort of ingrained in people's mind this idea that interpretability and performance, especially training time interpretability, is in conflict with performance. And we see this model as one of the first instances that's trying to just sort of knock this house of cards questions down. There's no, done the right way, there's no sort of trade-off between these two, and sort of design in the right manner. So we're sort of going to show that with this model, the performance of the model compared to an equivalent model that doesn't have any of our interpretability sort of losses or sort of secret sauces in there. And this allows us to sort of put two models head to head, one with our interpretability and one with the sort of next token predictor or a regular diffusion model. And so that's sort of one of the first things we'll show. The second one is the model is at the scale that it's actually useful for sort of various tasks. In the corpus, there's sort of a lot of legal document, financial document. The corpus is quite big. And so interacting with this interpretable models affords you a few different things that you currently are not able to do with standard models. And so one of the things we're actually eager to show people is with a single model, you'll be able to do three things. You'll be able to trace any group of tokens to the context. You'll be able to trace any group of tokens to these concepts that we talked about. And then lastly, you'll be able to trade into the training data. And so there's currently sort of no single model that exists that can do all three and can do them reliably at the scale that we're doing it. And so sort of showing this to people and now allowing them to be able to interact with a model they can control in three different ways is actually something we're very excited about.
Awesome. Well, that is quite exciting.
Yeah.
This has been great. Thanks a lot. I really enjoyed this and really informative.
No, this is great. Thank you for having me.